Okay, so good afternoon to all, and welcome to lecture number 11. Yesterday we talked about high-pass filter and how to detect the edges, and then particularly we focused on first-order derivative techniques like as a pivot operator, Sobel operator, or Krish operator, and so on. And then also at the end of the lecture, we have seen the Laplacian, that is second-order derivative technique for detecting the edges. Now, you know that the limitation of the first-order techniques are like, for example, some of the edges are missing, then noise is also present. In case of Sobel operator, the edge thickness is more, whereas in Roberts operator, some of the edges are missing, and so on. So that kind of problem is there. Whereas some of the problems are taken care by second-order derivative method, like as a Laplacian method. So it can detect the edges properly, but one main disadvantage of that Laplacian method is it is very sensitive to the noise. So a lot of noise is present in the image, edge-detected image, and you know that because of this noise is also high frequency component, special frequency component, and edge is also a high special frequency component. So it gets detected, and then you get the noisy edge image, and so on. So we need a very clean image or clean edge detected image, and so on. And this is taken care by basically we have to remove that noise, and we want only the image with only edges, and so on. So see that what happens, suppose for example here, consider a single row or a column of the image, and if you plot the intensity as a function of position, this gives the signal. Like for example, you have this single row like this, okay, means intensity is low up to this one, and then above it is high, and so on. This basically this or even you might have seen that in a case of two images, like for example, this is black portion and this is white portion, and then if you plot the edge profile, it will look like this way. But only thing is that this is not clearly black, because there are some noise present in the black portion, as well as there is some noise present in the white portion, and you get the noisy edge profile in this way. Okay, so if you apply directly the derivative function, that is the high pass filter, what will happen? So if you take the derivative of this, okay, you get basically derivative like this, okay, and then where is the edge? So it becomes very difficult to find out the edge in this case. So we are not able to find the edge in this case. So by taking this, suppose for example, this is the f of x function, which is noisy, and this is step edge basically. And then if you take the derivative of this one, you got this output. So where is the edge? Question is that. So it becomes very difficult to find out the edge. So what is the solution for that one? So we have to basically remove the noise from this function or from this edge profile, and then after that we can detect the edge, and so on. Now how to remove that noise? So you know that for removing the noise, you have to use the low pass filter, because edge is nothing but the this one. Your noise is nothing but the high special frequency component. So you have to remove that high special frequency component and pass this one through this. Okay, so definitely you will get the smooth image, or basically a image with good quality edge detected, and so on. So first we have to smooth that image. So for that we have to use the low pass filter. So you know that low pass Gaussian filter is nothing but the low pass filter. So if you apply a Gaussian filter, or if you convolve this H function with this F signal is nothing but the edge profile of the image, which is noisy, and if you convolve with this one, what kind of output you will get? So see that when you convolve this F with H, so definitely this noise will be removed, and then you will get very smooth edge profile of this image, right? So now after that, if you apply a high pass filter, that is nothing but the derivative operation. Here it is nothing but the integration operation or low pass filtering. So if you convolve this one H with F, you got this output, means your edge profile, which is corrupted by noise, is very smooth, and then noise is removed, and after that detecting edge will be very easy. So see that if you take the, see, this is the function, is basically this is the output of this one. When you convolve this f with h, means when you convolve or when you do the low pass filtering of this input signal, so you got the output that is nothing but the h is convolved with f. And now if you take the derivative of this one, so dou by dou x, if you take, you will get the function like this. Now where is basically h? So h is at this location, right? So h is at this location. So you can see that the at the peak of the this function there is a h or like that. Okay, so you can easily detect that the h in that case. So h is, so if you see here, where is the h? H is nothing but at the peak of this derivative of h convolved with f, right? So you have to look for the peaks in dou by dou x or h of h is convolved with f and so on. So you have to look for the peak for finding the h and so on. Now see that for example, this can be also done by taking the derivative of either you can take the derivative of this convolved function. See, what you are doing here, you are convolving this low pass filter with image or h profile. If you suppose, for example, if you are considering the f as the image, and if you are convolving that with low pass filter, and then you are taking the derivative of this one. So whatever you have done this operation, you got this output, right? So which is detecting age very clearly and so on. Now this is equivalent to what you are doing. You are taking the derivative of this filter. So derivative of this Gaussian, you got this function like this, and then after that you are convolving with this f, so you get the same output. So derivative theorem of convolution is also gives the same, means basically dou by dou x of h convolved with f is equal to dou by dou x of h convolved with f. So this operation is same kind of thing. And now so basically where is basically h is at the maxima function, or you can find out the local maxima of that function to find out the h location and so on. Now see that if you take the double derivative of that function, okay, so double derivative of that function, so this is the function basically input image or h profile of this one, which is corrupted with noise. And now you have what you have done here, you have taken the single derivative, and now if you take the double derivative of this one, you got this. So this is nothing but the Laplacian of Gaussian operator. So kernel function of this Laplacian of Gaussian operator, why it is called as the Laplacian of Gaussian? So Gaussian is h, okay, and then you are taking the double derivative, that's why it is called as the Laplacian. Okay, so Laplacian is nothing but the derivative, and then which function you have used? You have used this Gaussian function. See that here, this Gaussian function, you are taking the derivative of this Gaussian function like this. So this is the first derivative. If you take the second derivative, so you get the Laplacian operator. So second derivative is nothing but the Laplacian of what you are taking. You are taking the second derivative of Gaussian function. So you got the function like this. Now this is your original h profile, which is corrupted with noise, and then this is the Laplacian of Gaussian operator. Right now you are convolving this operator, this kernel, with the signal, this signal. So if you do the convolution, that is dou to h by dou h2, this is nothing but the Laplacian of Gaussian is convolved with the signal f. Now you got this kind of output. Now where is the h? So h in this case is at the zero crossing. So you can easily detect the h in Laplacian of Gaussian where there is a zero crossing. So here there will be a h, right? So zero crossing of the bottom graph gives the location of the h and so on. So this was basically the function in one-dimensional case, and then in two-dimensional case, this is the Gaussian function, two-dimensional case. And if mathematical formulation of this Gaussian function is given by 1/2 pi sigma square e raised to minus u square plus v square by 2 sigma square. So this sigma is basically gives the deviation of the standard deviation of this Gaussian function. Okay, so if you consider the larger standard deviation, you will be considering the larger area or more number of neighboring pixels. If you consider the smaller value of delta sigma, then okay, this will be having the low standard deviation, and then it will consider a smaller area or neighboring pixel and so on. Now, if you take the double derivative of this one, this function, then this double derivative of this Gaussian function, you get this one, this output, and this is basically single derivative, and then basically okay, Laplacian is nothing but you are applying this Laplacian operator. You are taking the double derivative of this function with respect to x and y, because this is a two-dimensional function. So you have to take with respect to x as well as partial derivative with respect to x as well as partial derivative with respect to y. Means already we have seen in yesterday's talk about this one. Even your first derivative operators like as Privet operator or Sobel operator or Krish operator. How do you do that one? You have separate operator for this one, the y component as well as x component. So here also you have basically this one. You have to do a partial derivative with respect to x as well as partial derivative with respect to y. So this is the Laplacian operator, and then this function is basically okay, so this is the Laplacian of Gaussian of this one. So this is single derivative, and then after that Laplacian of Gaussian. So this is double derivative. So you get the function like this for two-dimensional case, right? So for one-dimensional case, already we have seen that for one-dimensional case you get like this, and then when you convolve that one with this signal, you get the output like this. So here is the edge, means zero crossing is the point where there is a edge. Now, just you are extending this idea for two-dimensional case. So this is the Gaussian operator, and then you are taking the derivative of this first derivative, and then you are taking the second derivative. So you get the Laplacian of Gaussian. So once you get the Laplacian of Gaussian, just you have to convolve that one with your original image. Now, generally the operator which are designed with Laplacian of Gaussian are okay. This is also called as a Mars and Hilt edge detector. Okay, in Laplacian of Gaussian, another name of that one is also Mar and Hilt edge detector. So what is the step for doing this LOG, detecting the edges with LOG, Laplacian of Gaussian? So first thing is that first step is you have to smooth the image by using the Gaussian filter. Then you have to enhance the edges using the Laplacian operator. Then you have to find out the zero crossing which denotes the edge location, and use this in the linear interpolation to determine the subpixel location of the edge. Now this can be done, okay, automatically by using the LOG operator. So this Laplacian of Gaussian mathematically is defined as in case of two-dimensional, it is minus 1 upon pi sigma raised to 4, 1 minus x square plus y square divided by 2 sigma square into e raised to minus x square plus y square divided by 2 sigma square. So greater the value of sigma here, sigma tells the deviation, standard deviation of Gaussian filter. So if you are considering the larger value of sigma, then you are going to consider the more number of neighboring pixel in case of image, and then when you are considering the more number of pixel, you will get the more smoothing. Okay, more is the smoothing. But if you get more smoothing, what happens basically? Sometimes it may happen that edges may get blurred or something like that. So too much smoothing may make the detection of edges difficult. So you have to select the proper value of sigma, which will basically remove the noise as well as it will also preserve the edges and so on. So that is the basically job. So this is also called as the another name of Laplacian of Gaussian is also called as the Mexican hat operator, because it looks like as a inverted Mexican hat or something like that. Okay, so the mask which is derived from that Mexican hat operator is like this. So here this is the mask value of with sigma equal to 1.4. So you got this mask, and then just you have to convolve this mask with the original image. Okay, now okay, this can be also done, because see here the computational complexity is more in case of Laplacian of Gaussian, because you have to remove that noise with Gaussian function, then after that you have to take the Laplacian of that one, and then finally you have to take the edge and so on. So this can be done in alternate way, okay, instead of doing all those things, you can take the difference of Gaussian. Okay, so this is called as the DOG operator, difference of Gaussian operator. So because here LOG requires large computation time for the for a large edge detector mass, because your edge detector mass is large, then computation time will be also large in that case. So to reduce the computational requirement, approximate LOG by difference of two LOGs is nothing but the DOG. DOG means difference of Gaussian. So what you are doing basically, you are taking the two different values of the Gaussian function. Now, what is the Gaussian function? First Gaussian function is having sigma 1 as a standard deviation, and second Gaussian function is having sigma 2 as a standard deviation. So just you take the this one difference of that one, and then okay, once you get the difference of that one, okay, you apply it for the use it for detection of the edges. So definitely the result will be same like as the earlier one, but computation complexity will be less in that case. So advantages of Gaussian is DOG. It is close approximate of LOG and less computation efforts, and also width of the edge can be adjusted by changing the sigma 1 and sigma 2. Okay, so you can see the basically the this one different operators here. Now here, if you look at the second derivative techniques, so as we have seen in yesterday's talk, that second derivative technique method, especially Laplacian, if you are using only Laplacian, it is very sensitive to noise. You get the noisy image along with the edges and so on. And then there is chances that probability of false and missing edges may remain, and localization is better than the gradient operators, or localization is better in as compared to the gradient operator or basically simple first order derivative techniques and so on. Now just see the result of Laplacian of Gaussian filtering and then Laplace filtering. Okay, so LOG output, see that this what we have done here, we have used the LOG, means image is smooth by using Gaussian function, and then after that Laplacian is taken. So noise is less in that case. Here the image is not smooth first, directly Laplacian is taken, so you find that a lot of noise is there and misleading edges are there. So definitely the result of Laplacian of Gaussian is better as compared to the result of only Laplacian filtering. So this is the one-to-one comparison between the output of LOG and simple Laplacian filter and so on. Now see the output of this one, Gaussian versus derivative of Laplacian of Gaussian versus difference of Gaussian or derivative of Gaussian. So it is almost equal. Okay, almost equal you get, but here as I told you that computation complexity is less in difference of Gaussian or DOC operator as compared to LOC operator. So you can use either one as per your requirement. There is no chances of a noise here. Both images are really same and so on. So this is again another example. Only thing is that okay, here this zero crossing, you get the Laplacian of Gaussian filtering, and then this is the so zero crossings are more accurate at localizing, but not very convenient in this case. Okay, now the second order derivative edge detection, that is the drawbacks of differential method for edge detection. What are the drawbacks of this second order derivative? They are very sensitive to the noise. Okay. This has been reduced in the LOG or DOG method as compared to Laplacian. This is also not good for the ramp edges. Ramp edges means basically what kind of edge profile. So for example, you have a dark image, and then after that you have intensity has been gradually changing, and then again intensity remains same. So that middle portion is nothing but the ramp edge. So in that case, this is not good. This method are not good for detecting the ramp edges, and make no difference between the significant edge and the detailed edge and so on. So these are the limitations of second order derivative method, and this will be taken care by using the optimal edge detection criteria. So optimal edge detection criteria is nothing but your canny edge detector. So that we'll see. But before that, just quickly let me take the review of how to detect the lines or points and so on. So detection of discontinuities. Now, you know that there are three basic types of gray level discontinuities that we tend to look for in a digital image. Like, for example, whether there is a point discontinuity, or whether there is a line discontinuity, or whether there is an edge discontinuity, and so on. So to find out those, we typically find the discontinuities using mask and correlation. So different masks can be used for finding the point discontinuity or line discontinuity or edge discontinuity, and then we can find the correlation with image, and then from that you can detect that one. So see that point detection. So point detection can be achieved simply by using the mask below. So this mask, you can detect the point. Like, for example, here, this is the point, and then if you use this, so you'll get the result like this. Again, if you do the thresholding of that one, you can detect that this point very clearly. So points are detected at those pixels in the subsequent filtered image that are above a set threshold value. Means this is your basically a point detection mask. This one is your point detection mask. This is your X-ray image of a turbine blade with porosity. This is the porosity part, and then this is the result of applying this mask on this one. So you got this result. After that, what you have done, you have just set the threshold value, and then below certain threshold, this one intensity level, all the pixels are made 0, and above that one, all pixels are made 1. So after the thresholding, you got the result, and the result is such that it is detecting the point or the point in the image and so on. So in that way, you can detect the point detection in the computer vision. So this is very clear X-ray image of a turbine blade, the result of this point detection mask application, and then after thresholding, you get the output like this. So this is the output. Now, line detection. So you have to use the different masks for detecting the lines in the images and so on. So this is the next level of complexity. The next level of complexity is to try to detect the lines. The mask below, these are the masks which you can, so this mask will basically detect the line which is in horizontal orientation. This line, this mask will detect the line which is oriented in plus 45 degree. This mask will detect the line which is oriented in 90 degree, that is vertical, and then this mask will detect the line in minus 45 degree, and so on. So what you have to do is, when you have to detect the line which is oriented in horizontal, this one, so just to convolve this. So if you convolve this mask with the image, it will detect all the lines which are oriented in horizontal direction. So after convolution of this mask with the original image, you get output such that it will detect only horizontal lines in the image. If you convolve this mask, or if you do the filtering of the image with this mask, you will get all the images which are 45 degree oriented in the image. So that will be the output. Then if you convolve your image with this mask, then you will get, output will be detected as vertical lines. And similarly, output will be detected as minus 45 degree lines. So just you have to use the different masks for detecting the different orientation of lines. So you have detected the points, you have detected the different lines by using this one. So this is the output of this. So minus 45 degree, and then after thresholding, you get the result. So these lines can be detected, and though these lines can be used as a features in mid-level computer vision and so on. So summary, overall summary of this one is that first order derivative edge detection technique. This is simplest method, but what is the problem? Problem is that there is a noise as well as in Sobel edge detection technique. It is sensitive to the, or basically it is giving you the wide edge, or basically thickness of the edge is larger. Whereas second order derivative technique, which is very sensitive to the noise, but this can be also overcome, as I said, with the help of Laplacian, Gaussian, and so on. Another technique is there, okay, that is Hilbert transform based edge detection technique is also there. This is good for ramp edge detection, and also it has a better noise immunity, but bad for accurate detection, and so on, right? So the final champion of edge detection technique is your canny edge detection technique. Now, why canny edge detection technique is good? So we can see quickly. Now see that, as I told you that, suppose for example, this is your true edge, like, so these are the pixels which is representing the true edge. Now, our expectation is that, okay, edge detection method should be robust to the noise. Means basically whatever be the noise, it will not be detected as the edge. It will remove that noise first, and then it will detect the true image or true edge. Second thing is that, see if this is the poor robustness to the noise. Means suppose for example, if your true edge is like this, and if you are detecting the edge like this, means it is your edge detection algorithm is not giving the correct edge, it is giving the noisy edge or something like that, or some of the edge pixels are missing, whereas the edge pixels which are not there are detected as the edge, this one. So this is called as the poor robustness to the noise. So this is not good. We expect this kind of output. Second thing is that localization. See that your edge should be like this, but if your edge is detected like this, so this is called as a poor localization. So your edge detection should have a good localization, it should have a good robustness to the noise. And third thing is that too many responses. See that what is ideal? Ideal is like this, means we want only the pixels detected as an edge like this. We don't want this pixel to be detected as edge, this pixel or this pixel to be detected as edge. So if you are getting output of edge detector like this, so there is a too many responses. So our requirements are three requirements. One is our edge detection algorithm should be robust to the noise. Second one is it should have good localization, and a third thing is that it should have basically it should not have too many responses. It should detect only the true edge, and so on. So this has, okay, all those expectations are satisfied mostly by the canny edge detector technique which is proposed. So canny edge detector technique criteria one is that good detection, that is the optimal edge detector must minimize the probability of false positive as well as false negative edge. So that is good detection. Second criteria is that good localization. The edges detected must be as close as possible to the true edge. Means basically your localization should be good. It should not be like that, okay, numeric pixels are detected as the edge. Third criteria is that it should have the single response. It should not have multiple responses or too many responses. So the detector must return one point only for each edge point, and so on. Now, so there are 5 stages in the canny edge detector. So what you have to do, you have to convolve. You have to do the convolution with the derivative of Gaussian, then you have to do the non-maximal suppression, and then after that you have to do the hysteresis thresholding. Okay, so how canny edge detector work? Basically, you have to smooth the image, okay, by Gaussian function. So this Gaussian function is given by this one, right? After that, this will remove the noise. So noise removal procedure is done in step 1. Then after that, you have to take the derivative in x direction and y direction, right? So this is basically, see that this is S is the image, suppose for example, output image of what? This input image is I, which is convolved with Gaussian function that gives the S. Now this S is further, what is done? Derivative is done, taken. Now partial derivative in x direction and y direction is taken. So that will give you the Sx component, which is nothing but the derivative of this Gaussian function in x direction, and derivative of this Gaussian function output S in y direction. After that, you have to calculate the magnitude of this Sx and Sy. So that will give you the edge strength, and this will give you the angle, will give you the direction of the edge, so which is given by tan inverse Sy by Sx. So see, step is that first you are doing the Gaussian filtering. After that, you are taking the derivative of that Gaussian, and after that, you are finding the magnitude and then angle and so on. So see that this is the function delta S, which is given by what you are doing here. You are convolving this Gaussian with input image, and after that, you are taking the derivative of that one. So this is like this. So this derivative of this Gaussian function is nothing but your partial derivative in x direction and y direction, and then this delta S is nothing but you are taking what derivative of this Gaussian, and then after that multiplying with or taking the conversion with image and so on. So in same kind of thing. So see that this is the original image I, and then this is Sx component, that is nothing but your horizontal or x directional derivative after noise removal, and this is the Sy component, that is nothing but the y direction component. And see that after taking that one, if you take the magnitude of Sx and Sy is like this, so you get the edge detected image, and if you set some threshold value, you get the edge detected like this. So threshold value here is greater than 25 and so on. Now here basically as I said that non-maximal separation is used for giving the one response, not for many response. How it is done? So we wish to basically mark the point along the curve where the magnitude is biggest. Suppose for example this is the edge, but suppose for example other pixels are also on the edge, so we have to remove the other pixels and you have to keep only the pixel on the one pixel on the edge. So that for that you have to take the decision, and then this decision is done by non-maximal separation. So we wish to mark the points along the curve where the magnitude is biggest. So we can do this by looking for a non-maximal along a slice normal to the curve. So this is slice norm and normal of this one. So this is the slice and this curve, and then normal to this one is this one. Now these are the pixels of the edge pixels. Now we have to choose one pixel among them, which will give you the this one maximum response, and the pixels which are not giving non-maximum response will be suppressed or like that. So those points will form the curve, and there are two algorithmic issues at which point is the maximum and where it is the next one and so on. So for that non-maximal separation, like as I said that there are three pixels, which is giving the output as in the magnitude image as a edge pixel or like that. So one pixel is like as a xy is x comma y is the one of the pixel, and then the neighboring pixel x dash y dash is also giving the output as a high gradient magnitude, and also x dash x double dash and y double dash is another pixel which is also. So among these three pixels we have to select only one pixel because we want one response, not many response of this one. So this can be done by using non-maximal separation. So how it is done basically? So for that you are taking the maximum of this one. So how? So you will be comparing the response of this magnitude of this one with what? So magnitude of this one with x dash and y dash. If magnitude of this one is greater than so the magnitude of this one is greater than this one, then it will be kept like this. And also it's not only one. So you're also comparing magnitude of this pixel or intensity with this one. And if it is greater, then it will be kept like as a pixel on the edge. Otherwise, it will be 0. So x dash, y dash, and x double dash and y double dash are the neighbors of x comma y in the magnitude of delta S along the direction normal to an edge. So that now suppose for example it may happen that like for example you are comparing this one and then you got maximum response here, right? As compared to xy or x double dash. So then at that time you have to keep the x dash y dash as a pixel on the edge, and you have to remove those 2 pixels. Or sometime it may happen that x dash x double dash and y double dash is having maximum magnitude as compared to x y or x comma y or x dash y dash. So at that time you have to keep this one. So out of these three you have to basically choose one, and then this is taken based on the value, intensity value or magnitude value, and the pixel which is having more magnitude value will be kept as a pixel on the edge or something like that. Okay, now okay, so for angles also it is taken like as a maximal non-maximal separation. So tan theta of s of sy by sx, so you are going to take so 0 direction will be equal to minus c, if minus 0.4142 is less than tan theta is less than minus 0.4142, then this pixel will be considered as a edge direction as 0. If it is okay, if it's in the range between 0.4142 to 2.41, then this will be considered in the direction will be considered in this one, and then for tan theta greater than 2.4 on this one, then it will be considered in the direction 2, and then minus 2.4142. If tan theta is in between this one, then the direction of that pixel will be considered as a 3. So 0, 1, 2, 3, this direction will be based on the angle of that as pixel, right? So in that way, so after non-maximum suppression, if you see the result and with the threshold you get the output like this. Then hysteresis thresholding is used for, so for example, sometimes it may happen that there is a break in the this one edge, like some of the pixel is missing. Now how to take whether that so for example edge is like this and then this center pixel is missing, so we have to fill that gap. So this filling this gap, it can be done by using hysteresis thresholding. How? So just you have to compare the neighboring pixels, and if neighboring pixels are having high intensity, greater than intensity, then you have to assume that the pixel under consideration which is missing is also a pixel, H pixel or something like that. See that. One thing is that means basically here hysteresis thresholding is also done for taking the decision, like whether that magnitude of okay, if magnitude is greater than the high value of threshold, then that pixel is certainly on the H pixel, right? See that magnitude of that pixel. See, you have two threshold value. One is high threshold value and another one is low threshold value. If pixel magnitude is greater than high threshold value, then that pixel is considered as a surely it is a pixel of H. If threshold value, okay, if pixel is having threshold value in between, okay, or basically below low value, then that pixel is certainly not a this one. H pixel. But if the intensity of that pixel value is in between low threshold value and high threshold value, so like that way, so see that if pixel intensity value is in between this range, then okay, as I said that if pixel value is above that high value, then that pixel is considered as a H pixel. If that pixel intensity value is or magnitude is greater than this less than this low value, then that pixel is not considered as H pixel. But if pixel value is in between low and high, at that time how decision is taken? Okay, their neighboring pixels are considered. In that case, if neighboring pixels are on the edge, then that pixel will be considered as a H pixel. See that for taking the decision whether that pixel belongs to H pixel or not. If it is above threshold value, then it will be 100% H pixel. If it is below threshold value, it is 100% not a pixel. But if it is between 0 this one low and high, at that time you have to consider the neighboring pixels, and in that neighboring pixel, if they are on the neighboring pixels are H pixel, then that pixel will be considered as a H pixel. Otherwise it will not be considered as a H pixel. So like that way. So hysteresis, if the gradient at the pixel is above high, declare it as a H pixel. If the gradient at the pixel is low, declare it as a non-H pixel. And if the gradient at a pixel between low and high, then declare it as an H pixel if and only if it is connected to the H pixel directly or via pixel pixels between low and high. So in that way, hysteresis thresholding is done in the canny edge detector. So this is see that threshold value greater than 25 and then high threshold value is considered as a 35 and low threshold 15. You get the edge detector like this. So then after that, finding the connected components. So basically, if any component is missing, then you have to see the neighboring and then you have to connect the component and so on. So scan the binary left to right from top to bottom, and if there is an unlabeled pixel P with value of 1, assign the new label to it and recursively check the neighbors of pixel P and assign the same label if they are unlabeled with value 1. So stop when all the pixels with the value 1 have been labeled. So like this way, this one, canny edge detector works. So if I summarize this canny edge detector, first step is basically you have to do the Gaussian filtering. Then second thing is that you have to take the x derivative and y derivative. After that, you have to take the magnitude of that one and then angle of that one. After that, you have to do the non-maximal suppression and then hysteresis thresholding and then finding the connected components. So these are the 5 steps basically which are used in canny edge detector, and canny edge detector performs better as compared to the other edge detectors. So this is all about the edge detection, first order as well as second order we have considered. In our next lecture, we'll see how to find the edges by using in multispectral images, as well as how to find out the edges by using scale space approach. So in our next lecture, we'll we'll study that one. So thank you very much.